Hello, everyone. This is Spencer Snowling from Hatch, and I'm glad that you can join us today for our webinar. We're very excited to be presenting today. Myself and my colleague Jacob Barkley are here to talk about what is new in the new version of GPSX, version 9.0, that will be coming out next week. So it's always an exciting time. I'm always really happy when we have a new version coming out and I get to do the webinar and we get to talk about all of the new cool things that we have been working on over the past couple of months. So there are enough new things in this new version that we've actually had to spread it over 2 webinars. So you'll see here that today is part 1, and then about a month from now, towards the end of May, we'll be doing another webinar, part 2. That will cover all the remaining material. So what I'll do is, as per our usual methodology with our webinars, is we ask if you have any questions about things that you see along the way, you can type them in the chat window. So put them in the chat and we'll proceed along and collect the questions as we go. And then when we get to the end, I'll have a few words about some other things going on at Hatch, and then we can stick around, Jacob and I, and answer a few questions live at the end of the webinar. Okay, so let's jump right in. So what I'm going to do is we're going to start by talking about how you go about getting the new version 9. I'm going to talk for a little while about the new interface features that are available, and Jacob's going to jump in at that point and talk about some of the new process models that we have done, particularly in this case talking about process controllers that you can add to your model and to operate your facility in a realistic way. And as always, we will be doing a number of desktop demonstrations along the way. And as I mentioned, we will answer questions at the end of the webinar that you have put into the chat. Okay, so let's talk about how you can get the new version. So unlike previous versions of GPSX when we released them that required you to get a new key code and so on, it's actually very straightforward now under our new licensing system. So basically, when you start GPSX, there is an update option. It's actually available from the help menu. You can say check for updates. And you will, if you do this next week, you will see announcing the release of version 9.0. And on there, it actually has the instructions of what you need to do. It has a link that will take you directly to the place that you can download the installation software. So we're going to make it available starting Monday. Now, actually, if you have the default installation of GPSX, it'll automatically do this for you the first time you start it up next week. But if it doesn't do that for whatever reason, you can use the help menu and get check for updates. Now, I will say there are some people who have told us that their local company's firewall has gotten in the way of doing this, and you may see a message saying that I can't connect. If that is the case, please just email us at the support, and then we will give you an email and give you all those same directions as we go. Okay, so once you've got that download package, you can install it and then run, and then you can log in using the same email and password that you were currently using for version 8.5. So all users who have an active GPSX license right now are entitled to the upgrade to version 9 immediately. And as I mentioned, you can install that right away, and you can actually keep your older versions of GPSX installed if you like. There's nothing stopping you from doing that. If you're halfway through a project right now and you don't want to switch on the fly, you can keep your 8.5 going as needed. Okay, so let's get into the new stuff. So as you may remember in previous years, if you've been a GPSX user for some time, we tend to group our new things that we put into each software upgrade into interface features. So things that make it easier for you to build your model, run simulations, plot the data, and all of that. So there's an interface side that we work quite a bit on, and we have a number of new features there that I've shown on the screen, and I'm going to go through those today. That includes process benchmarking. We have a new simulation log functionality and some changes to the way that we read data in and so on, some new features in the scenario functionality. And then on the other side, we have the wastewater content. So almost always, I think, just thinking back now, I'm thinking pretty much every single release of GPSX that I can think of, we've had new objects that you can put on the drawing board. And in this case, this year, we were focusing on things that will help you set up and operate the plant in a bit more realistic kind of way. So there's a number of new controllers that are there and things that can schedule things to happen on a regular basis or on a random basis. And so those things are new that you'll see. Jacob will be demonstrating a couple of those this week and a couple of those next month. In addition to that, we have a number of other features that have updated. We have a new ORP model that is available. So any place you're on your drawing board, you can calculate what the ORP would be at that point. A new runoff model, the Australian water balance model, that is there to kind of mimic a rainfall on a watershed and having a bit of a surge of flow to the plant after a rain event. Some things to have a sort of a hydraulic delay in the plant and some updates to our chemical dosage model. And then we've updated the calibration of the GPSX models in several ways. Some of these are very minor and very specific, and there's a couple of them that I'll come and talk about next month that are, done for a specific reason. And so we'll cover off all of that material just so that you can get a handle on what to expect. And of course, there's always the assorted bug fixes and minor interface improvements that come along with a new version. So I'll give a shout out to all of our users who have contacted us since we put out version 8.5 a year and a half or 2 years ago that have said, hey, it'd be really great if there was a button here that did this, or can this menu be changed to do something else? And we really appreciate all that feedback. It helps make our software really good, and we have passed on that to our programmers, and we have really made big efforts to be able to listen to what people have suggested and make those changes and updates accordingly. Right. Okay. So now, as I mentioned, that's everything that's new in version 9. We don't have time today to squeeze all the demonstrations in. So we're going to do about half of this today, and we're going to do about half of it next month. So I'm going to talk right now about the new interface features, and there's 4 of them that I want to talk about. And the first one being process benchmarking. Now, this is a feature, it sounds simple, it's straightforward in its application, but it is actually very useful and valuable. It is a new functionality where we are adding color to some of the outputs in the middle part of the quick display panel. This is the part where we have, some of those key process indicators like overflow rate and sludge blanket height and so on. And we are now applying a coloring system to those so that you can be alerted when something seems out of the ordinary. Maybe you wouldn't have noticed if we didn't have this coloring system in place. And any other places where we have variables that have benchmarks, and you're also putting those on the digital display, that will also be benchmarked as well. So, you may use that where you've opened up an output variable menu and you've dragged a bunch of variables onto one of these little digital displays, kind of making your own table, so to speak. And you'll see there that the colors get applied there as well. Okay, so let's talk about how this works. We have basically ranges of colors, as you can imagine. And they're defined by objectives and upper and lower limits. So if you fall in the middle here between the minimum and maximum objective value, then it will be green, as it's shown in some of these examples here. If you're too high or too low, but not past the limits, then it's yellow. And if you're off the top or off the bottom, then it will definitely be shown in red. So the idea is that there's sort of ranges of values, and this, it works independently of whatever units you want to work in. And we have applied these, and the coloring works accordingly. So one thing that you can do to understand what's being applied is to just hold your cursor over that colored value, and it will pop up in this little tooltip window what those limits are, so that you can look at the number and also compare it to what is on our limits, and then you can see sort of where it falls and what your expectations might be. Right, so that is kind of a neat and handy thing. It just happens automatically. You don't have to do anything. It's part of the new upgrade to this functionality. Now, all the other stuff that's not colored, if you just see any other values, that's just the regular model prediction. If it's black, it means we're not applying any benchmark values to it at all. So that's just working the way that it always has. Right. Okay. So where do these benchmarks come from? So there is a spreadsheet that we have stored away in our resources folder, along with many other things that are user editable functionality that you can make your own personal changes to in your GPSX. We have created a spreadsheet, and it is basically a large table, as you can imagine, of all of the variables that we wanted to apply benchmarks to. And we have our sort of, mins and maxes here available. We are telling you what units that we're working in, and then in most cases there is a reference over here regarding where we got that from. Now, you'll see many lines in this spreadsheet that are blank as well. So what that means is we've left a spot for you to add things if you want to do that. We decided that it would be good to kind of make this as flexible and easy to use as possible. You can come and edit this spreadsheet. You can change these benchmarks if you don't want to work with these ones. If you want to have your own set, that's fine. You can also add to and start benchmarking other things that we are not currently providing in this first draft of this functionality, and you can come in here and make those changes. The only thing that I do mention is just note that we're doing this in the default GPSX units, which are going to be metric units, and you can see those units here. So you just need to work out whatever your benchmark values are in those units, and then restart GPSX after you've saved the spreadsheet and closed it. And then GPSX in the software, you'll then see the benchmarks applied in any other units as you flip from one to the other. So I want to say a couple of words, though, about what the benchmarks mean. So these are there for the purposes of alerting to you to things that don't look like maybe it wasn't set up properly, right? So it is, not uncommon to have a value, say I've entered a flow rate in the wrong units. So it is, an order of magnitude bigger than it should be, kind of thing. It's easy to do that. And so we put these highlights in so that we can make sure that somebody understands, oh, there's a value that I didn't actually put the real number in that I meant to, or I've entered a number, but I did it in the wrong units. These are not design guidelines. These are not intended to be your clarifier should have this particular loading rate. These are instantaneous sort of checks, benchmarks, just to make sure that values are kind of like as you would expect them to be. So therefore, when you're running dynamic simulations, we're continually updating things. So you may see the colors actually dynamically change, but they're certainly not a design guideline where it's got a safety factor built in and all of that kind of stuff. So basically what we're saying is these are here to help you identify anything that looks weird that you might have not noticed. And just to help you point out things that you might want to have a second look at. If you choose to say, no, I'm okay with that number, I'm just going to move forward, that is totally fine. It doesn't have any effect on the model outputs. It's just a color that we're applying to the results. And if you don't care for it, we can actually turn it off. So there's in the View Preferences menu, the benchmarks will be selected on, but you can actually just turn it off and it will go back to working like it did previously. Okay, let's take a look. So we're going to do a quick demo here. So I've got a layout that is open. So this is just a typical BNR layout here. And so I'm going to run it to steady state. And so as I mentioned, the places that you're going to see this is by looking at the quick panel. So I'm going to double click on this clarifier here. And as I mentioned, it is actually in this middle panel that we apply these benchmarks. So it's been an interesting process putting it together. We couldn't put as many benchmarks in as we wanted to because there are many things that sort of don't have a benchmark, or the way that we use that object a lot in GPSX is like so generic that we can't really apply something. But the clarifier is a good example where we're actually doing this in a kind of interesting way. So you can see here, obviously, these are all in the acceptable range. That's all looks quite good. So I'm going to rerun this with a higher influent flow rate. So let's do that. And I'm going to rerun it to steady state again. So by increasing that flow, I'm increasing the loading, I'm increasing the surface overflow rate. So once we get the new solution here, what we're going to do is we're going to see how the coloring works out. So now this is the example that I actually took the screenshot of that I put in that slide. So you can see here, we've got some examples where we are we're over the objective, but under the limit. And then we've got the sludge blanket height, which is actually almost, 3 feet tall there. It's close to a meter. That's obviously something a little higher than we would expect. And so if I hold the cursor there, you can see that it's greater than 0.9, which means it was flagged as being red. So pretty straightforward functionality. We hope that you find this useful, and we are eager to hear your feedback on that. Okay, back to the slides. Now we're going to move on to a new feature that we have created, what we call the simulation log window. And this is actually a reorganization of where some of the output comes when you're running your simulations. This is a new window that will show up at the bottom of the screen for you. Sorry, at the amongst all of the tabs, and there's an image on the bottom of the screen here. And that simulation log, the purpose of it is we're directing a lot of the output that comes from the model and also sort of logging the work that you were doing there automatically. So it shows you how long it took to run simulations, any other warnings or alarms that are generated from our models, and many of them have a built-in thing saying, hey, you've selected the wrong option for this kind of aeration or so on. That kind of stuff gets printed. It used to get printed to the command window. We're now putting it in its own special window. And anytime something happens, it will turn red and alert you that you should take a look at this tab and see what's going on. So we still have the command window. That is now pretty much solely just for doing command line interactions with your model. It's one of the more advanced features in GPSX, and not everybody uses it, but it still has that same functionality and works the same way it did. It was just that it was starting to get really cluttered up with a lot of information. So we've now separated out all of that interactive stuff and the steady state solution information and all that stuff into the command window, and then all of the stuff related to actually running simulations and the actual wastewater information into the simulation log here. Right. Okay. Now bringing that up, because we've added a new feature that uses this simulation log and helps you sort of do a little bit of data cleaning and to handle a little bit more consistently the information that's coming into GPSX. So in version 9, we changed the default behavior of the sliders and the file input controllers when things were falling outside of these minimum and maximum bounds that we had put on that slider there and on the file input controllers. So previously, if you had come in and typed a number that fell outside that bound, say it was above the 100 that it's showing here, we would highlight the number in red, but we would still use whatever number you had and then put that in the model and go ahead. But it wasn't done in a completely consistent way between some of the various functionalities inside GPSX. So what we've done is we've now made it all completely consistent in the way that we're doing it. And I think it actually is better in this sense that it is now doing it the way that I think most people intuitively want it to be done, which is if I have a bound, I want you to apply it. So that's what we're doing now. So if you have a number that you're typing in here and is above the bound, we're going to cap that and apply that bound value. If you're reading in some data from a file input, we will actually do that there as well. So if you read in a number that is above that upper bound, then we're going to cut it off and just use that max value. So if that happens, if something falls outside the min or the max when you're reading the data file, we are actually going to start logging those. So in a way, what we're doing is we're calling that outlier logging. Anytime that you apply what we call an outlier above or below your boundaries, it will now turn the simulation log red, and it will print out a little warning for you. So when you're running a simulation, it always tells you which file that it has read in, the one that it's using. And then also it's going to start generating these things. And you'll note here it says the file input value was out of range at time equals 1.0 days. And the file value was 154, but the max was 100. So we used value was actually used was 100. So consistent way of applying the numbers into the system, and also we are logging them there. So if you have a giant file with the hundreds and hundreds or thousands of data points, and one of them was an outlier and you didn't know, then it's a nice way to be able to lay your hands on that and just correct that, something that might be a little bit out of the ordinary. Okay, so let's take a look at that in action. So I'm going to flip over to my other demo I have here. It's basically the same plant. And what we're going to do is I just want to show you here what this looks like. So if this is now at a max of 60 grams per meter cubed here of total TKN. So if I put in something that is greater than 60, if I put an 80, for example, and I hit enter, you can see that it maxes out at 60. And it actually, even though I typed 80, it's actually showing 60 here now. So again, we're trying to do this in a more sort of consistent way. Okay, so now I'm going to show you this. Just let me reset that. I'm going to show you a scenario that we have created where I'm going to read some data in. So you can see here the data is being read in. This is the look of the controllers when data is assigned. So I'm just going to show you the data file itself. So we go to data files, and we go to edit. And so this is one that I set up previously. And so once this opens up, you can see here, I'm just reading in these 3 columns of data. And we got this one number right here. So it's 134. So I set this up. I have imagined a situation where I meant to type 34, but I typed 134. So this is clearly an outlier. And what we do is we want GPSX to identify that and not use all of that number. So yeah, let's close this up. And let's run this 3-day simulation here. And we'll take a look at what the simulation log has to tell us. So if I go over to that page, you can see the first thing is it's read in this, and it's telling us that's the spreadsheet that it is using. It's telling us that the dynamic simulation has started here. And when we get to the beginning of the second day, which will be at 24 hours here, these numbers will change to the second line of that spreadsheet. So they've done that now. And you can see that it's identified that was a problem. As you remember, it was 134, but now it's actually just applying the max of 60 that was there. And here, oops, it's a bit of a long message. Here's our message identifying that that has happened. So pretty straightforward functionality. I really quite like it. It's kind of helped just to make things work better. Okay, and lastly, I got a couple more slides that I want to show here. We now have some new input controller properties that can be saved into a scenario. So I highly recommend that you take a look at our scenario feature webinar that we did, I think, 2 or 3 years ago. If you're not familiar with what scenarios are, but just to give it a 1-minute explanation here, basically a scenario is when you create a name and then you save a number of input changes to that name, and it allows you to do that in a temporary way, define that temporary scenario that I want to run, and then easily move between them without having to open up a lot of menus. You can assign data files to each scenario. So this is a typical thing that most GPSX users use. It's quite a popular feature, but the only thing we ever saved in a scenario was the value of a constant, right? So a value of an input. But now what we've done is we've basically saved the type and setup of the controllers themselves as well. So this is very handy because what it's telling us is we can have different scenarios and you can apply different min and max bounds and different types of controllers for different scenarios. So now the main reason we did this is to allow people to very nicely set up a sensitivity analysis. You may use the analyzer feature in GPSX to do automatic sensitivity analysis, but it was something where you would have to go in and tell for this parameter, I want to have this analyzed and I want it to go from this value to that value, et cetera, et cetera. That can now all be saved in the scenario itself. So it's quite good. You can also temporarily inactivate things that are on controllers as well, just by unchecking them. And that allows you to sort of just gray out a scenario, a particular value for a particular scenario. You're saying, I don't want to read this value for this particular scenario, or I don't want people to make any adjustments in this scenario, but I don't want to have to completely delete it and then have to add it back again later. So it's temporary inactivation is what we're doing there. That can be done in the base scenario, or you can actually do it and save it as one of the features of this new stuff that you can save into these scenarios. Okay, one last demo for me here. Let's show what that looks like. And I know this is for a relatively specific thing, but I think actually for users of scenarios, they will enjoy that. Okay, so what I'm going to do is do that sensitivity analysis. That's basically something that I think is handy. So here's where we were working from before. I'm going to create a new scenario, sensitivity. And this might be one that we were doing for a sensitivity analysis. And so now if I'm doing that, I want to set this up so that, say, the influent flow can be adjusted from some range, but I don't want to necessarily do 0 to 10,000, but I want to make changes here. So I can go to the properties, I can go here to analyze step, and I can say I want to adjust this from 500 to 2,500 in steps of 250. And then when I hit accept, this is now saved in the format that we need. And if I went ahead and did the sensitivity analysis, I would turn on that right here and then run the steady state. So I'm not going to do the sensitivity analysis, but I did want to show you that this can be configured. And now because I did this in a scenario, it's been saved for that scenario. So if I go back here, and I go back to the base model, it returns back to the normal setup that I would have. So it's nice to be able to have everything ready and set to go, and I can flip to when I want to do scenarios. I can make multiple different scenario definitions, have everything configured nicely, and I can run through those quickly, and it's very, very handy. Okay, so I also want to say, for example, that I'm going to go back to that dynamic example where we're reading data in, but let's say I don't want to read in the orthophosphate concentration this time. I can actually just quickly inactivate that. And then now here you can see that that one's not going to be used in this scenario, but if I flip back to the base model, it comes back again. Okay, so that's new GPSX functionality from all the interface side that has actually been added. And I'm going to come back and probably talk about a few minor things when we do this again a month from now. But here you go. And now at this point, I'm going to pass things over to Jacob, who's going to talk about some of our new process controllers.
So yes, as Spencer mentioned, I'm going to be talking about some of the new process controllers that are included in GPSX version 9. So in GPSX version 9, we've included 5 new process controllers: a proportional controller, a step controller, a weekly scheduler controller, a conditional controller, and a discrete event controller. In this particular webinar, we're just going to focus on the proportional and the step controller. We'll touch on the other 3 in our part 2 webinar a month from now. So first, let's take a look at the proportional controller. And just to illustrate what this controller actually does, we just have a very simple example here to illustrate the purpose of this controller. So when you're using this controller, you're going to have a signal that's going to be your control variable. So in this example, that's going to be flow A. And what the controller does is it takes that control variable and then multiplies it by some proportional constant that you specify, and then your manipulated variable is going to be held at that particular scaled value. So for example, if we want to calculate a flow B and we want that to be equal to 200% of flow A for our proportional constant, then we can specify it in the controller, and it's essentially going to give us a signal that is double what flow A is for flow B. Or if we want it to be 50%, then it's going to produce a manipulated variable signal for flow C that's equal to half of flow A. And then as flow A proceeds and it does things like increases, then our manipulated variables will also increase. And as our flow A control variable decreases, then our manipulated variables will also decrease, all scaled to that proportional constant. So this is what the proportional controller object looks like in GPSX. And we only have one model available for this proportional constant, our proportional model. And what this model's for is to create that proportional functionality, where this was something that was already available in GPSX, but only in very select applications. So some of you may be familiar with the proportional options that were available for pumping RAS, for example, in our secondary clarifier object. We had included that there because it is a very common application, but by adding this object, we've expanded it out so that you can use the proportional functionality for any variables that you want in GPSX. So you can use any variable in GPSX to be specified as your control variable, and then you can use that control variable to specify the proportional value of any input controls in GPSX. You're not limited to just very specific spots, but you can pick anything that you want now. And all of this functionality is handled in a single input parameters menu, this controller settings menu, where this input menu looks like this, and kind of the key functionalities of it are a controller setting where you can toggle the controller on and off, a field where you can enter what your control variable cryptic tag is going to be, where that's the entire cryptic tag, both the prefix that's created by GPX by default and that label that you add to every one of the connections in GPSX. You can also specify a manipulated variable where that's also done by just entering in the complete GPSX cryptic tag. And you can specify what your proportional factor is going to be for a given manipulated variable. So you can have multiple manipulated variables and they can all have different proportional factors in this one controller. Then you can also specify a default value that's going to be used if you turn off that controller so that your manipulated variable will be held constant at this value when that controller's off. And in each proportional controller object, we offer the ability to specify 5 distinct manipulated variables that you can change through your simulation. The other new controller that we're going to touch on is the step controller object, where just a illustrative example of how this is going to work is you have your flow that is going to be your control variable signal in this case, and then you specify a control variable logic or a controller logic for that step controller, where that's done by specifying a discrete number of zones. So in this case, we have 3 distinct zones that we want to control. You specify a upper boundary for each one of those zones, and then you specify a value for the manipulated variable when the control variable is in that particular upper boundary. So for example, here we have a 1,000, 3,000, and 6,000 upper boundary. So those are shown on this plot. And what the controller does is it uses the most restrictive upper boundary. So this particular signal would be both the 3,000 and the 6,000 boundary would be appropriate, but since the 3,000 meter cube per day boundary is more restrictive, it's going to use that and set your manipulated variable to a magnitude of 1.5. If the control variable signal were to increase so that it's now above that 3,000 meter cube per day upper boundary, but below the 6,000 meter cube per day upper boundary, then it's going to use that 2.0 manipulated variable set point. And then if it falls below the 1,000 meter cube per day boundary, even though all of the boundaries are now true, it's going to use that most restrictive one and assign a value of 0.5. So the step controller object model looks like this in GPSX, and it also has just one mol available to it, where this allows you to define distinct control actions for the discrete control variable ranges that you want to specify, where you have the control to specify how many of those ranges and what their upper boundaries are going to be. And you can use any variable in GPSX to be your control variable. And then just like the proportional one, you can kind of specify any GPSX input variable to be your manipulated variable. You can specify distinct control actions for each one of the boundaries for each manipulated variable. All of this is done through a single input parameters menu, our step controller setup, where it looks like this. And the key features are a toggle to turn the controller on and off, the ability to specify how many distinct zones you want in your step controller. You can specify your controller sampling time, where this is how frequently the controller stops, take a look at what the value of your control variable is, and then assign or update manipulated variable values if appropriate if your control variable is in a different zone, for example. You can specify what your control variable is, where that's done with the entire cryptic tag, and then you can specify your manipulated variables using the entire cryptic tag. To actually specify what your control logic is going to be, it's going to be in this manipulated variable array menu, where when you click on that ellipses button, it's going to open up a menu that looks like this, where it'll have a column pre-populated with the zone number, where that's going to correspond to the number of zones that you specified in the step controller setup section. A section where you can specify all of your upper boundary conditions. It's important to note that this is done using the SI units or the default GPSX units when you're specifying any of these values. And then you can specify the manipulated variable value that you want to be used when you're in that particular zone. And then we also offer the ability to specify up to 15 different manipulated variables in a single step controller object. All right, and now we'll take a look at a few desktop demonstrations to show off these controllers in action. All right, so first we're going to take a look at the proportional controller, where this is the plant that we're going to be looking at. It's just a very simple plant where we have a influent, primary clarifier, a conventional activated sludge system. Our secondary sludge is being thickened, where our primary sludge is being sent to a primary sludge holding tank, and then the primary sludge and the thickened sludge are being sent to a belt filter press. So now if we move into simulation mode, we can take a look at doing some simulations. So right now our controller is on, and if we go into that proportional controller in our input parameters menu, we can take a look at what our control settings are. So right now our control variable, what we want to be making all of our proportional changes based on, is our influent flow. So that's going to be this this stream right here, our influent flow rate. And what we're controlling is we're controlling our pumped sludge from our primary clarifiers and our pumped sludge out of this primary sludge holding tank. So right now, those are both specified with a proportional factor of 0.5. So anything that's being pumped out of the primary clarifier is being sent to the primary sludge tank and then being immediately pumped out. And when the controller is turned off, both of those have a fixed value of 10 meters cubed per day. So now if we run that simulation, we can see what would happen. So our influent flow is just using a repeating daily diurnal pattern that has an average value of about 2,000 meters cubed per day. And if we now take a look at our primary sludge plots, you can see that this is what's being pumped out of our primary clarifiers. It's just recreating that influent pattern, but at a much smaller scale because we're only pumping 0.5%. And then here's what's being pumped out of that primary sludge tank, where it's the same diurnal pattern as our primary sludge pattern because we are also doing a proportional 0.5%. This plot shows what the volume of our primary sludge tank is. Right now, it's being held constant at 100 meters cubed. It's important to note that this tank has a maximum volume of 250 meters cubed, so it is only partially full at the moment. And then you can see that we aren't actually overflowing anything from this tank because everything that's being pumped to it is also being pumped directly out. So now let's see what happens if we were to increase the amount that we're pumping out of that tank. So if we set that to be 2% of our influent flow rate, increase our stop time, and continue that simulation, you can see that our primary sludge pumping rate immediately increases to be 2% of our influent flow rate. And now that we're pumping more out of that tank than we're sending in, then our primary sludge tank volume begins to decrease. At about a little after 9 or 8 days into our simulation, we actually empty out that tank entirely. So then our pumped flow automatically drops back down to just match what's being pumped in, as there's no longer any extra volume inside of that tank that it can pump out. So now if we were to reset that proportional factor for what's being pumped out of this tank and increase our pumped flow rate from our primary clarifiers, for example, and we increase our stop time to 20 days and continue that simulation, you can see now we are pumping more primary sludge from this primary clarifier than we're actually pumping out of our tank. So our tank volume is increasing. At about 19 days into the simulation, we've reached the maximum volume of that tank. So then we start to see some overflow happening. But because we've specified the pumped flow rate to be constant at that 0.5% proportional rate, so we start to see some flow overflowing out of there. And the final thing that we'll take a look at with this particular example is what happens when we turn off that controller. So if we increase the stop time and continue that simulation, you can see now both the flow being pumped out of the primary clarifiers, our primary sludge, and what's being pumped out of this tank are being fixed at 10 meters cubed per day, because that's what we specified the value to be when the controller is turned off. And since those flows are now matching again, our volume in our tank isn't changing, and we are no longer overflowing anything from that tank. All right. So the next thing we're going to take a look at is an example with the step controller. So we're using the same layout here with a couple of modifications. So we're no longer using the proportional controller. Now we have a step controller icon. And internally, our aeration tank has been changed from conventional activated sludge to now using a 4-stage Bart-and-Faux process. So we're going to take a look at comparing the different ways that we can aerate this tank. So the very first thing that we'll take a look at is what happens if we just specify the entering airflow. So what we're going to do is specify a constant airflow rate and a constant distribution to the 4 tanks in our our bioreactor. So we're always going to be providing the tanks with 12,750 meters cubed per day of air. So if we run that simulation, we can see that our airflow rate is constant at that specified value, but our DO concentrations in the various tanks are changing quite dramatically throughout the simulation because we're always providing that same amount of air, even though we do have a variable influent flow rate. So our DO concentration is changing throughout the simulation. Another thing to note is that we are nitrifying, but our ammonia in the effluent is changing quite a bit throughout that simulation as well. So it's ranging between about 0.1 to 0.25 throughout that simulation. And the final interesting thing to note is that over this 5-day period, the cost of using this aeration strategy is about $220. So we can take a look at a couple of different aeration strategies. So for example, we could specify a constant DO set point. So we're going to use a DO controller to fix the DO concentration in zones 2 and 4, our aerobic zones, at 2 milligrams per liter. And then zones 1 and 3, we're just going to set at 0.1 just to offer a little bit of mixing in those tanks to account for that. So if we run another 5-day simulation, you can see that now that we're using a DO set point instead of a constant airflow rate, our air is varying throughout the course of that simulation period. But one thing you can note is that in our aerobic zones, our DO is much more stable at our set points of 2 milligrams per liter. And another interesting thing is that our effluent ammonia is a lot more stable as well because we now have enough oxygen available at all times throughout the simulation. We don't have periods of low DO concentration. So it's much more stable, having a range of about 0.08 to 0.12. And an important thing to note is that our energy cost is more or less the same because we're providing very similar amounts of aeration over the 5-day period, but it's much more directed to when it's actually needed. So the final thing that we're going to take a look at is actually using our step controller to perform ammonia-based aeration control. So I'm going to turn that on and we can take a look at what the logic of this controller is. So if we go to input parameters, step controller setup, and then click on this ellipses button for our manipulated variables, we can see what our action is. And what we're doing is we have a control variable that is the ammonia in the third tank of our aeration basin, and then we want to manipulate our DO set points based on that ammonia concentration. So we've specified that there's going to be 4 zones, so we have 4 rows in our array, and we've specified a couple of upper boundary conditions for the ammonia in the third tank. So we have 0.5 milligrams per liter, 1 milligram per liter, 2 milligrams per liter, and 20 milligrams per liter, just to have a large value that's going to catch anything that exceeds that too. We're going to hold our zones 1 and zone 3 DO set point at 0.1, and that's just to offer a little bit of mixing air. And then for zones 2 and 4, we have our control logic that we want to use. So if our ammonia in tank 3 is less than 0.5 milligrams per liter, then we're going to set the DO set point in those tanks to 0.1. If it's greater than 0.5 milligrams per liter, but less than 1, then we'll set it to be 0.5 milligrams per liter for our DO set points in both of those tanks, and so on. So if it's between 1 and 2, we'll have a DO set point of 1, and then otherwise we'll have a DO set point of 2. All right, so now if we actually go about running that simulation to see what will happen, you can see just like when we're using a DO controller, our airflow rate is variable to meet the DO concentration despite the changing influent flow rates. But where it differs from using a fixed DO set point is now we're actually changing the DO set point, which you can see in that red line, and our DO concentration is reacting to that. And all of that is based on our ammonia concentration in the third tank. So you can see it is variable and it's jumping between the various zones. So at some points it's below that 0.5. At some points it's below or between 0.5 and 1 milligram per liter. And then at a couple of points it is exceeding that 1 milligram per liter zone boundary. So that's why we are changing that DO concentration throughout. And you can see that using this ABAC controller is pretty much as effective as using that DO controller. Our ammonia leaving the tank is a little bit higher. It ranges from 0.1 to 0.15, but it is better than using a fixed aeration, airflow rate, and it is very similar to our ammonia concentration using the DO controller. And it's also more efficient. It's cheaper. We're saving about $20 over that 5-day simulation period by using this ABAC controller instead of using a fixed DO controller. All right. I'm going to hand it back to Spencer now to wrap up our webinar.
Thank you, Jacob. So just quickly to summarize, as we've arrived to sort of the end of this series of demonstrations, is just to let you know that, as always, when we release a new version, we have updated both the software interface side and also the wastewater modeling content side. And so we were able to or we really had a focus this time around on like making things easier for you to set up and use the models. So this idea of benchmarking is there to kind of help you identify places where maybe you need a little more attention about a particular parameter that you are using, to do that outlier logging, to just point you to any problematic information that might be read in from a file, to use that scenario input control just to make your life easier when you're trying to run certain kinds of simulations and not having to go back and turn things on and off so much as needed. And then also to do a much more complex controller design and to operate the plants in a more realistic way. So to be able to implement more advanced controls. So as Jacob said, we've always had the ability to do that, either through some very specific menus that do things. And of course, we've always had our the ability to write your own code in GPSX and add that. But we were seeing that a lot of people were building certain kinds of controllers on a regular basis, and we are doing that for our own projects as well. So we've implemented a whole new set there just to make it so that you can do that in your own models much more easily.